Hello, guys. Let me try to finish chapter 2. Let's see how far I can go. All right. Last time we talked about omitted variable bias. Okay, this is very severe issue in econometrics. I showed you that. So suppose we have 2x in our true model, but we omitted 1. In this case, we can know that the sign of the omitted variable bias, all right? But next one, how about if the true model contains x1, x2, and x3, which means 3x, but we omitted x3, okay? The bad news is with more than one included x, we generally can't say which direction the bias goes. We don't know the sign, okay? We don't know the direction. It's not a simple plus or minus rule anymore because x3 can be correlated with x1 and x2 at the same time in complicated ways, all right? So there's no general statements possible about direction of bias. But the analysis as in simple case if one regressor uncorrelated with others. Okay, so that's a shortcut. If one of the included x is uncorrelated with the others, we can analyze its bias just like the simple two-variable case. Okay, so here is the simple two-variable case. Let's look at the example, the wage example. Wage, okay, so here we're omitting ability in a wage equation like I mentioned before, right? The ability, wage equal beta 0 plus beta 1 education plus beta 2 experience plus beta 3 ability plus mu. Suppose we omit ability, okay? Normally, this is the messy with 3x. But if experience is roughly uncorrelated with education and ability, we can ignore experience for this purpose and analyze education's bias exactly like before. Just check the correlation between education and ability, same as the simple case. But remember here, we assume that if experience is approximately uncorrelated with education and ability, then the direction of the omitted variable bias can be analyzed in the simple two-variable case, okay? Which means last slide, all right? This is the simple two-variable case. Let's continue with our assumption. Okay, so here we have one more assumption, which is assumption 5, homoscedasticity. The simple meaning, okay, the spread of mu must stay the same, no matter what values the x take. So say here, VAR means variance of mu I given xi1 all the way through to xik equal sigma squared. The value of the explanatory variables must contain no information about the variance of the unobserved factors. So here, remember assumption 4, MLE, MLR, assumption 4. Assumption 4 said that average of mu doesn't depend on x, okay? And here, MLR5 adds the variance of mu, how spread out the errors are, also doesn't depend on x. Which means how spread out the errors are. Also doesn't depend on x. Okay, one is for the average, another one is for the variance. Which example again? Here, the variance of mu given education, experience, tenure equal sigma squared. In plain words, our prediction errors should be equally unpredictable for someone with 5 years of education and someone with 20 years. Okay? The slide notes this is actually hard to justify in real life. Think about it. For example, wage tend to vary a lot more for highly educated people since some go into high-paying jobs and some don't. While low education wages tend to cluster more tightly, so this assumption often fails in practice. We'll deal with that later when we cover heteroscedasticity. The bottom line, okay, shorthand notation, variance of mu I given xi equals sigma square with xi equal xi1, xi2 all the way through to xik. So you notice that x here is uppercase, right? So xi here just bonds all the x together in one vector. Same idea, just shorter notation. Theorem 3.2, okay? So now that the assumption 1 to assumption 5 all hold, we can ask how precise is our estimate, beta j hat. That's what this formula tells us, okay? Variance of beta j hat equals sigma square over SSTJ times 1 minus rj squared. Three things derive this. Let's build intuition for each. The first one is the error term, which is the sigma squared. This is the variance of the error term on top, right, or on the numerator. More noise in mu means less precise estimates. Does it make sense? A noisy world makes everything harder to pin down, okay? So here, because sigma square means the noise in mu. Next one, SSTJ. This is the total sample variation in explanatory variable xj. On the bottom, which means if xj barely varies across your sample, say almost everyone has the same years of education, OLS have very little to work with, so the estimate is imprecise. More spread in xj means more precision. Bigger sample size also generally rises SSTJ, which is part of why more data helps, okay? So let me write it down. Which means more data helps. Next part, RJ squared. This is the new important one. Okay, so let's see R squared from a regression of explanatory variable xj on all other independent variables, which means xj on all other x, okay? And including a constant, this means that it's the R squared from regression xj on all the other x. In words, how well the other x can predict xj. If xj is highly correlated with the other x, rj close to 1. If rj close to 1, then 1 minus rj squared shrinks towards 0, right? And the variance blows up. This is the price of collinearity. Even imperfect but strong collinearity, while not violating our assumption 4, remember? MLR assumption 3, MLR assumption 3, it says that no perfect collinearity, okay? So here, let me emphasize the imperfect but strong collinearity while not violating MLR3 still makes your estimates much less precise with wider confidence intervals and less reliable results. So 3 ways to get a more precise estimates. We always want less noisy in mu. Okay, we want less noise, more spread in xj, and less overlap between xj and the other x. BTW means between xj and the other x. Okay, so this slide breaks down the 3 components that I just mentioned before from the variance formula. Okay, the first 2, let's see. The error variance, all right, the error variance, I'm gonna use blue. Sigma squared, more noise in mu, higher sampling variance, less precise estimates. Important point is that this is unavoidable, okay? This is unavoidable. Unlike the other pieces, sigma squared does not shrink just because you collect more data. If the underlying world is noisy, it stays noisy no matter how many observations you add. It's here. A higher error variance increases the sampling variance because there's more noise in the equation, and the large error variance necessarily makes estimates imprecise. And also, the error variance does not decrease with sample size, okay? It means that even if you get more observations, more data, it doesn't help to reduce the error variance. This is unavoidable. Next component, the total sample variation in XJ, SSTJ. More sample variation leads to more precise estimates. Total sample variation automatically increases with the sample size. Increasing the sample size is thus a way to get more precise estimates. Okay, here's a question for you guys. Why? Why increase the sample size is a way to get more precise estimates? Because SSTJ automatically grows as N grows. More people, more spread, more signal, right? We want more signal, less noise. This is one of the main reasons we always want bigger samples in econometrics. And here I need to emphasize a little bit. So I hope you still remember from your statistics. Basically, we have two laws, right? What it says, used for what? The first one, law of large numbers. In short term, L, L, N. And another one, central limit theorem. So for law of large numbers, it says that as n goes to infinity, the sample average converges to the true mean. We use it for consistency. Your estimator hits the right target. Next one, central limit theorem. It says that as n goes to infinity, the sampling distribution becomes narrower and more normal. Okay, the sampling distribution becomes narrower and more normal. This is why you will hear a lot about normal distribution later. So this, we use it for the precision. Okay, which means your estimator becomes more reliable. Okay, that's why increasing the sample size is thus a way to get a more precise estimates, because central limit theorem. Okay. Next one, the third component, and the one that connects back to what we discussed a little bit ago. Remember Rj squared, right? Rj squared. This is the one that will regress xj on all the other x. This R squared tells us how well can xj be predicted from the other x, okay? See the highlighted part. The more xj can be explained by the other x, the higher the sampling variance of beta j hat. Because if the more xj can be explained by the other x, that means you have a high multicollinearity, all right? Makes sense with our partitioning out picture. Still remember partitioning out? If the other x already explain most of xj, there's very little pure independent variation in xj left over for OLS to use, so OLS gets confused. Less clean signal, less precise estimates, okay? And here, the problem of almost linearly dependent explanatory variables is called multicollinearity, all right? Which means Rj squared, here I need a squared, tends to 1 for some j. Okay, here let me repeat it again. Rj squared close to 1, we call this multicollinearity. Important distinction from before, okay? This is not a violation of MLR3, assumption 3. MLR3 only bans perfect correlation. Okay, only best perfect correlation between x, which means rj squared equal 1. See the difference? One is equal 1 exactly, but another one is close to 1, okay? Maybe 0 0.8, 0 0.85. Multicollinearity is the imperfect but severe case. Rj squared close to 1, but not quite equal 1. Okay, this model is still technically valid. OLS still runs, but your estimates become very imprecise with huge stand errors, even though nothing is technically broken. Okay. Let's see a real example of multicollinearity. So here we have our y-average standardized test score of school. Here x1, expenditures for teachers, x2, expenditures for instructional materials, and x3, other expenditures. You see here? The different expenditure categories will be strongly correlated because if a school has a lot of resources, it will spend a lot on everything. It will be hard to estimate the differential effects of different expenditure categories because all expenditures are either high or low. For precise estimates of the differential effects, one would need information about situations where expenditure categories change differently. As a consequence, sampling variance of the estimated effects will be large. What does it mean here? What does it mean here? The average standard test score of school equal expenditure for teacher, expenditure for material, and other expenditures. Think about it. If schools with more resources tend to spend more on everything at once, right? More on teachers, more on materials, and more on other things too. So these three X move together strongly. So the consequence is that it's very hard to tell which specific category actually drives test score. To separate their effects cleanly, we would need to see cases where, let's see, teacher spending goes up, but material spending stays flat. But in real data, in the reality, that almost never happens. They rise and fall together. The result is that OLS can still estimate the model. Nothing is technically broken like MLR3 assumption violation, but the sample variance of each beta will be large, wide, unreliable estimates, even though the regression runs perfectly fine. Okay, we can run the regression, but we're gonna have higher sampling variance for each beta. Okay, will be large. Let's continue. So here, let's see the discussion of the multicollinearity problem. In above example, it would be probably be better to lump all expenditure categories together because effects cannot be disentangled. Lump means combine, okay? So maybe we just combine them together. My computer got stuck. Let me see. Something wrong here. So right now you can hear me, but you can't see my face. Okay, so let's just wait a few seconds. I'm gonna fix this. I'm still here. Please bear with me. Just wait for me, okay? Sorry about it. So you may review what I just covered, okay? Think about this example here, right? So here's an example of multicollinearity. Let me open my Zoom on my computer. Zoom. Okay, got it. Hello. Okay, I need to leave computer. All right, I'm back, but I'm not sure it's still recording or not. Okay, still recording, that's good. Okay, you can see my face. You can hear my voice. All right, good. Okay, let's continue. So here, two practical takeaways for dealing with multicollinearity. The first one, in the school spending example that I showed you here, since the categories move together so tightly, it's probably better to combine them into one variables, okay? Which I showed you here, combine them into one variable, total expenditure, rather than trying to separate teacher spendings from material spendings. If the data can't tell them apart, don't force the model to try. Let me repeat it again. If the data can't tell them apart, don't force the model to try it. Don't force OLS to run it. You just get noisy, unreliable individual estimates for something you can't actually answer with this data. This is the first point. Second one, in other cases, you could try you could try dropping one of the correlated variables, so reduce multicollinearity, but important warning in parentheses. This may lead to omitted variable bias. All right? This brings us right back to the omitted variable bias problem we just learned. If that dropped variable actually belongs in the true model, you've traded one problem for another. Okay, so there's a real trade-off here. Keep all variables and accept some multicollinearity, or drop one and risk omitted variable bias. You have to think about it, okay? You have to balance the trade-off here. There's no free lunch. The right choice depends on what you know about your specific variables and what you are really trying to answer. Okay? If you keep all the variables, of course, you're gonna have a multicollinearity for sure. But if you decide to drop one, you may have the risk about omitted variable bias, okay? That's why in my homework, I asked you, please explain multicollinearity and omitted variable bias, okay? So now you may have some idea about them. So here are three quick wrap-up points on multicollinearity. The first one, only the sampling variance of the variable involved in multicollinearity will be inflated. The estimates of other effects may be very precise. Okay, only the sampling variance. Second one, the multicollinearity is not a violation of MLR3 in that strict sense. And also, multicollinearity may be detected through variance inflation factors in short-term VIF, okay? So here is the formula for VIF. As an arbitrary rule of thumb, the variance inflation factor should not be larger than 10. So 10 is the threshold value for VIF. Notice here, this connects directly to Rj squared we just learned. If Xj is well explained by the other X, Rj squared close to 1. So in this case, where VIFJ blows up. Okay, rule of thumb here should be the cutoff, okay, the threshold of 10 is a rule of thumb, it's not a law, okay? It's a rule of thumb, it's not a law. Now we bring bias and variance together. This is the real trade-off behind deciding whether to include a variable. Suppose we have a true population model, which is with 2x, okay? And estimated model 1 include both x1, x2. All right, so we have, because here is the estimated, so we have hat here. This is correctly specified, so beta 1 hat is unbiased, but remember, including x2 means less pure variation left in x1, so beta 1 hat has higher variance, okay? Let me write it down here. Beta 1 hat, in this case, is unbiased. But higher variance. Let's see our estimated model 2. So in this case, we drop x2. So here I'm going to use tilde, okay, tilde, y tilde equal beta 0 tilde plus beta 1 tilde x1. So here we drop x2. In this case, okay, so if x2 actually matters, okay, if x2 actually matters and is correlated with x1, beta 1 tilde is biased. But here, our assumption is that if x2 actually matters and it's correlated with x1, so in this case, our beta 1 tilde will be biased from omitted variable bias, but there's a payoff, okay? The variance of beta 1 tilde is smaller. Since we remove a source of collinearity, see here, it might be the case that the likely omitted variable bias in the misspecified model 2 is overcompensated by a smaller variance. So the key insight on the slide is that sometimes this smaller variance in model 2 can actually outweigh the harm from bias. In other words, a bias but precise estimate here. Variance just means how much precise, okay? How much precise. So here we have, because this is higher variance, so less precise. Let me write it down for you. The other way around, the variance here, variance beta 1 tilde is smaller, which means more precise. Okay, so here we see sometimes a biased but precise estimates can sometimes be closer to the truth, but on average, okay, than unbiased but very noisy one. This is the classical bias variance trade-off, okay? This is the classical bias variance trade-off, one of the deepest ideas in all of statistics, not just econometrics. There's no universal answer for which model is better. It depends on how big the bias is versus how much variance you save. Let's compare the two models. Okay, let's compare two models variance directly. The first one, variance beta 1 hat equals sigma squared divided by SST1 times 1 minus R1 squared. This is from model 1 with X included, okay? Model 1. And the next one, variance beta 1 tilde equals sigma squared SST1. This is from model 2 without X2. So notice model 2's formula is missing the 1 minus r1 squared term in the denominator, right? Since 1 minus r1 squared is always less than 1, because r squared is between 0 and 1, okay? That's why 1 minus should be less than 1. Dividing by it makes model 1, okay, makes model 1's variance bigger because you are dividing something that is less than 1, so the variance here gonna be bigger. So model 2's variance is always smaller. Dropping x2 always buys you some precision, no matter what, because we drop x2. Now, two cases, depending on whether x2 actually matters. The first one, beta 2 equals 0. That means x2 truly irrelevant, right? So in this case, both models are unbiased, okay? So this one is unbiased. This one is also unbiased. The same accuracy, but model 2 has smaller variance. Okay, the tilde is from model 2. This is from model 1. Okay, so in this case, model 2 has smaller variance. So here it's a clear win. If beta 2 equals 0, that means we drop the irrelevant variables. No downside, only a precision gain. Okay, so do not include irrelevant regressors. This only happens if beta 2 equal 0. Another case is that beta 2 doesn't equal 0. That means x2 truly matters, right? In this case, model 1 stays unbiased, but model 2 becomes biased. Okay, so here biased because doesn't equal. For beta 1 tilde, model 2 here still has smaller variance. You see here variance beta 1 tilde less than variance beta 1 hat. But now we are paying for the precision with bias. All right? Let me recall it. This is the real trade-off, highlighted in red, okay? The trade-off between bias and variance. Smaller variance versus some bias. Important caution is that the bias in model 2 does not shrink as your sample size grows. More data won't fix this, ever. Variance shrinks with more data, but bias is permanent, okay? Let me write it down. So in large samples, the case for including x2 becomes much stronger, since the variance advantage of dropping it matters less and less, while the bias problem never goes away. Same as simple linear regression, right? Because sigma square, we've been using sigma square the whole time, but in reality, we never know it. We have to estimate it. So this slide shows how. Remember, sigma squared hat equal summation of the error term squared divided by n minus k minus 1. In simple linear regression, we divide it by n minus 2. But here we divide it by n minus k minus 1. Not just n, okay? So here why we subtract k minus 1? Because we used up k plus 1 degrees of freedom. Okay, DFS means degrees of freedom estimating beta 1, beta 0 hat, beta 1 hat, all the way through to beta k hat. So basically, here is kx, right? And here is our intercept. That's why k plus 1. So think of it like this. Once you estimate all those parameters, the residuals aren't fully free anymore. They are tied down by the equations used to feed the line. N minus k minus 1 is called the degrees of freedom. The numbers of genuinely independent pieces of information left after fitting the model. Why not just divide it by n? I think I explained to you already. If we did that, our estimate of sigma square would be too small on average. Okay, so here means biased downward. Because we haven't accounted for the parameters we already used up. So dividing by n minus k minus 1 exactly corrects this. Okay, next one, the theorem 3.3. Under MLR1 to MLR5, the expected value of sigma squared hat equals sigma squared. This confirms with the right denominator, which is n minus k minus 1, our estimate is unbiased too. Okay, unbiased estimator of the error variance. If we know the error variance, what is the next step? And also it's the last piece, okay? We're gonna connect everything together into something we actually compute. The estimation of the sampling variance of OLS estimates, okay? So here, SD is the true sampling variation of the estimated beta j. So we just square root the variance of beta j hat, right? Okay, square root this formula. This is the true standard deviation of beta j hat, but it depends on sigma square, which we never actually know, okay? This is unknown. So in practice, we plug in sigma squared hat for the unknown sigma squared, okay? Our estimates from the last slide, okay, from here. Instead of the true sigma square, so this gives us stand error of beta j hat equals square root of the variance beta j hat. So in this time, this is our estimated variance with hat, okay? So here is the standard error. This is the number when you run the R programming, R will actually report in your regression output, okay? It's our best real-world estimate of how much beta j hat would bounce around across different samples. Let me help you with the vocabulary. Standard deviation means the true unknown quantity. Standard error which is our estimated computable version, you will see standard error of beta j hat constantly once we get to hypothesis testing. It's the key ingredient for t-statistics and confidence intervals. Last warning, okay, important. All of this is only valid if MLR1 to MLR5 hold, especially homoscedasticity. If homoscedasticity fails, this SE formula is simply wrong, and any tests or confidence intervals built on it would be unreliable. We'll deal with that problem later in the course. We will cover heteroscedasticity, robust standard errors, okay? Next one, and this is a big one, the Gauss-Markov theorem, one of the most famous results in econometrics, because we already know that under assumption 1 to assumption 5, OLS is unbiased. But here, a new question. Is OLS the best unbiased estimator? Turns out there could be many other unbiased estimator out there too, but which one should we actually use? To answer that, we narrow the search to a specific family, which is linear estimators, okay? So we only consider linear estimators that are a linear function of y. Look at the formula here. Beta j tilde equals summation wij times yi. This just means take each yi, multiply it by some weight, wij, and added them up, okay, because we have summation here. The weights, wij, can be any function of the x. That's very flexible, but yi itself must enter in this simple added up way, okay? So yi must enter in this simple and added up way. So why restrict to linear estimators? All these different possible weighting schemes, which one gives the smallest variance? That's what the Gauss-Markov theorem answers next. Okay, so we want the smallest variance. Here is the actual theorem, and it's a beautiful result. Theorem 3.4, Gauss-Markov theorem. Under assumption 1 to 5, the OLS estimators are the best linear unbiased estimators, which is blues of the regression coefficient. Break down the acronym, okay? Linear means beta j hat is a linear function of y, and I just showed you before, okay, here. Is a linear function of y, okay? Unbiased means the expected value equals the true one. Best, what does best mean? Among all linear unbiased estimator, OLS has the smallest variance, okay? So here, smallest variance. So here, variance beta j hat is less is smaller or equal to variance beta j tilde. So here's another estimator. For every other candidates beta j tilde you could dream up. In plain words, okay, so if you are restricted to unbiased linear estimator, OLS is guaranteed to be the most precise one possible. You literally cannot do better. No clever reweighting scheme can beat it. As long as our 5 assumption holds, okay, as long as our 5 assumption holds, actually, this is a very strong, reassuring result. It's why OLS is the default choice in econometrics, not just tradition. Okay, it's the default choice in econometrics, and it's the starting point of estimator that we use in econometrics. But critical warning at the bottom. This best title only holds if assumption 1 to 5 are all true. If homoscedasticity fails, for example, OLS loses its best status, other estimators can then beat it in precision. This is exactly why later in the course, when we relax MLR5 will need new tools like weighted least squares or robust stand errors. OLS prowess as best isn't unconditional. It comes with conditionals attached. Okay? Okay, so here if there is heteroscedasticity, we have better estimates. Let me show you. Maybe weighted least squares or robust stand errors. Okay. All right. So I'm not gonna show you the proof of LLS estimator, okay? Because if I show you about this, you will be more confused and hate more about econometrics. I don't want you to hate this course, okay? So basically, I just want to give you some intuition about econometrics. But we need to do some numerical calculation of LLS estimator. So here, please remember that in general, in matrix form, the OLS estimator beta hat equal X transpose X inverse X transpose Y. We will use this formula to do the numerical calculation later, all right? And I'm done for today. And a lot of information as usual. So please review this recording. If you don't understand, you can watch it again and again. If you have any question, you are welcoming to discuss with me. All right. So have a nice weekend with my recording, and I'll see you next Monday. Bye bye.